Welcome to the Deep and Better channel. In today's episode, we will see how genetic algorithms work using the classic knapsack problem. As an example, we will discuss the principles on which these algorithms are built, implement one from scratch, and apply in practice. Let's get started. Genetic algorithms are an optimization techniques inspired by evolutionary processes in nature. They utilize mechanisms such as selection, crossover, and mutation to iteratively transform a population of problem solutions, striving to find the best possible outcome. This makes them effective in solving complex problems where traditional methods might fall short. Genetic algorithms consist of several key components that collectively form the entire optimization process. These include the genome, the initial population, the fitness function, selection, reproduction, crossover, mutation, and iteration. The genome is the basic representation element in genetic algorithm, consisting of a string of bits, numbers, or other data. Each genome represents a single possible solution to the problem. Genomes are crucial because their structure determines the algorithm's ability to effectively search the solution space. The initial population is a set of randomly generated genomes that serve as the starting point of genetic algorithm. Each individual in this population is a potential solution to the problem. Diversity in the initial population is important because it increases the chance of the algorithm finding an optimal solution. The fitness function evaluates the quality of each individual. It determines how well a given genome solves the problem. The fitness function is crucial because the algorithm uses it to decide which solutions are better and should be preserved. Selection is the process of choosing the best individuals from the population based on their fitness values. Individuals with higher fitness have a better chance of reproducing. The selection process mimics natural selection, where the best adapted organisms have the greater chance of survival and passing on their genes. Reproduction is the process of creating new individuals based on their genomes selected in the selection process. New individuals are created by combining the traits of the parents, which allows the best genes to be passed on the future generation. Reproduction ensures the continuous improvement on the population toward better solutions. Crossover allows for the exchange and combination of traits between parents, leading to the creation of new, potentially better solutions. This process increases genetic diversity in the population. Mutation is the process of randomly changing the gene in an individual genome. It is used to introduce new traits into population, preventing stagnation and allowing the exploration of new areas of the solution space. Mutation is a key to maintain genetic diversity and avoiding local minima. Iteration is a complex cycle of processing in genetic algorithm involving selection, reproduction, crossover, and mutation. Each iteration leads to the creation of new generation, which should be better adapted to solving the problem. The interactive process continues until the optimal solution is reached or determination criteria are met. After this theoretical introduction, it's time to apply this knowledge to real-world computer program. The problem we will use an example is a classic knapsack problem. It involves selecting items, each with a specific weight and value, to maximize the total value of the selected items while not exceeding a specified weight limit for the knapsack. Packing all items is not an option, as their combined weight exceeds the knapsack capacity. The number of items and strategies for selecting them are not easy to determine, and the optimal solution depends on the specific set from which we choose. So let's move to the programming environment to write code that will find this solution for us. Before we start, Let's import two Python modules, random for generating random numbers, and pandas, which offers a range of tools for operating on datasets that resemble table in structure. In our knapsack problem, the fundamental element is a collection of items, each characterized by two values, weight and value. We will create a pandas data frame object from a set of random pairs of numbers ranging from 1 to 100. Each row will represent one item. We can see how they are presented. For convenience, let's transpose the object. We will set the weight limit of the knapsack by assigning its value to the variable. We will create genomes using the list filled randomly with Boolean values, true and false. These values indicate whether an item at a given index is in the knapsack or not. A natural consequence of this method of encoding information in the genomes is that the genome and the list of items from we choose have the same length. However, we need an entire population of individuals with random genes. To achieve this, we will create a function that repeats the above operation a specified number of times, returning them as a list. The next step will be to define the fitness function called fitness, which evaluates the quality of genome passed as a parameter. To achieve this, we will need to track two parameters: the total weight to check if it exceeds knapsack limit, and total value, which determines the quality of solution. In the loop, we sum weights and values of only those items of which the gene's value is true. Finally, we return total value provided that the total weight does not exceed the limit. Otherwise, we return value of 0. The next key element is selection. This process will be enclosed in a separate function, selectWinners, which returns genes with the value greater than 0, those that contains items but do not exceed the limit. Finally, we sort them by their values from highest to lowest using the sort function and the lambda expression. Additionally, when performing selection, we want to choose only the portion of genes, the set that has proven to be the best solutions to the problem. Since the selectWinner function already provides the sorted list, we can select initial elements representing a certain percentage of entire population. To do this, we will create another function, selectBest, which accepts filtered genes, the entire population, and the factor that specify the percentage of population allowed to reproduce as arguments. Before we proceed with reproduction, we have to determine how we will perform crossover. Combination the information contained by winning genomes and passing it on the next generation. To do this, we will create a crossover function, which takes two genomes as arguments and split them at randomly selected point in two parts. The new genome is created by combining the first part of first genome with the second part of second genome. Each newly created genome has a certain chance of mutating. To achieve this, we will create a mutate function which performs this operation. It accepts a genome as an argument, then change the value of the gene to opposite at a randomly selected point, returning the mutated genome. However, as we mentioned earlier, only a small portion of the population undergoes mutation. Therefore, we should perform it with relatively low probability. To do this, we will create the mutate randomly function, which only performs a mutation method with certain probability. In most cases, it leaves the genome unchanged. Having developed almost all mechanisms, we can create the method that generates the next population based on individuals that have undergone selection. We can create the next generation function, which accepts the selected population as an argument and then returns a new, equally sized population as a result. Before returning the new population, we must perform initial selection using the selectWinner function. If we obtain any valuable solutions, we can narrow the set down to 20% of the population with the best result using the select the best function. In the loop, we complete the new population with new individuals created using the crossover method and two randomly selected parents from the previous generation. When adding them, we randomly perform mutation using mutate randomly. If, however, no genome survives the initial selection, we create new random population, hoping that its random solutions will be more successful. With all elements presented, we can run the simulation. We will create the population of 1000 individuals and simulate their evolution for 20 generations. We will analyze the final generation to see which items are most frequently selected in its solutions. To do this, we will present the population as a pandas data frame object and obtain a column representing mean of their values for each item. Boolean values converted to 0 and 1, allowing us to calculate the mean and then multiply by 100 to get the result in percentage terms. We combine the column with the items object, ensuring proper column naming, and then display the result in transposed form. The correct solution is even more visible if we plot a bar chart of selection rate column for each item. In today's episode, we moved from theory of genetic algorithms through the implementation of key components to their application in solving Knapsack problem. Genetic algorithms, though powerful, are just one of the tools available for solving complex optimization problems. In practice, there are many ready-made frameworks that make it easier to work with such algorithms or with the broader family of evolutionary algorithms. That's all for today. Thank you for your attention and see you in the next episode.